Hello, this is a video about the Qibec 1-bit 1-instruction transistor CPU that you can see right here. In this video we'll walk through a simple program execution on the whiteboard, where you can see using arrows what exactly goes on inside the RAM and inside the CPU with respect to the program counter and the contents of the RAM. So the purpose of this video is to get a feel for what goes on between the CPU and the ROM and the CPU and the RAM during program execution. The actual system setup containing a ROM and RAM and the Qibec CPU is not discussed in this video. For example, how the RAM is connected to the ROM is not discussed here. For that, see another video please. So let's go. And I apologize in advance for the focus artifacts that will of course take place, but I'm using my phone for now, and so let's see how that goes. Now, as a summary, first let's write down what happens in pseudocode during instruction execution, during execution of one instruction every cycle. First of all, the data bit is inverted, so the data bit is replaced by its inverse. Then, if the data bit is 1, the program counter is simply incremented. Let's write it like that. Else, so after inversion, if the data bit is 0, the program counter is replaced with some branch address. Right? The meaning of the branch address, program counter, and the data bit, the data channel of the CPU, is not explained in this video, so please see another video for that. At the end of the instruction cycle, the whole cycle is repeated. The next data bit is inverted and so on. So let's take a look at the components of a system with ROM, RAM and the Qibec CPU. First, the ROM. Unfortunately, I'm right-handed, so you'll have to wait a little bit until I'm done with the drawing. Right, ROM is a block basically, which has an address input. And for now, let's assume there are 3 cells, 3 ROM cells. Focus artifact, never mind. So the address determines which ROM cell is selected, 0, 1 or 2. Yeah? Next up is the CPU itself. It's also a block. Let's draw it like that. It has a program counter output. Furthermore, it has a branch input. And it has a data I/O channel. Yeah. The program counter output is basically the next instruction in the program to be executed, or the currently executed instruction. Location of the currently executed instruction. Yeah. The ROM will provide the branch address. Branch is an optional next program location, right, as we will see. Actually, as you can see right here. Yeah. Furthermore, there's a RAM. Looks a lot like the ROM. It is also a block. It also has an address input. In this case, it's the ROM that selects the RAM address. Let's assume the RAM has 2 cells, and once again the address selects between RAM cell 0 or 1. Huh? Right. So remember from previous video that each ROM word can be divided into 2 fields. Each ROM word is 32 bits, each field is 16 bit. the leftmost field in this picture will contain a branch address in each instruction, so that is an optional next program location. The rightmost field in each ROM word will contain a data address, and we will see that that is exactly a RAM address, right? And in this video we'll use very small values. Now let's write a minimal program. Right. A very minimal program. Remember, these are not bits, 0 and 1. These happen to be 0 and 1, but in fact they're 16-bit numbers each. Yeah. Let's assume for now that the initial RAM content is 00. It doesn't really matter, but that's easier. In the reset state, the CPU's program counter is made 0. That means it starts executing at program address 0, program location 0. So the address of the ROM is set to 0. That means the ROM word 0 is selected. So the branch input becomes 1. The RAM address is also 0. That means that the RAM cell 0 is connected to the CPU's data I/O channel. Yeah. So at this state the CPU is ready to start executing. So what happens during execution? First, data bit is inverted, so let's do that. 0 becomes 1. After that, if the data bit is 1, the program counter is simply incremented. Well, the data bit is 1, so the program counter increments from 0 to 1. When that happens, ROM cell 1 is selected instead of 0. And when that happens, the RAM address becomes 1, so RAM cell 1 is connected to the CPU's data I/O channel. So now the CPU has executed one instruction. Now let's start executing the second instruction. Once again, the data bit is inverted, so 0 becomes 1. After that, the data bit is 1, so the program counter simply incremented from 1 to 2. ROM word 2 is selected. RAM address 1 is selected. It was already selected, so nothing else happens. Next instruction cycle. Data bit is once again inverted. After inversion, if the data bit is not 1, so if it's 0, then the program counter is replaced. The value of the branch input is copied to the program counter. Program counter is replaced with a branch value. Branch value, as you can see, is 0. So in this case the program counter becomes 0. And when that happens, ROM cell 0 is selected again. And because of that, RAM address 0 is selected again. Like that. So CPU is ready to execute yet another instruction, so let's do that. Data bit is inverted, 1 becomes 0. After the inversion, data bit is 0, so the program counter is replaced with a branch value. Branch value in this case is 1, so the program counter becomes 1. That means that ROM cell 1 is selected, as you can see. That means that RAM address 1 is selected, as you can see. Next instruction cycle. Data bit is inverted again, 0 becomes 1. After the swap, data bit is 1, so the program counter is simply incremented from 1 to 2. ROM cell 2 is selected. Starting to become a mess, but we're almost done. And RAM address 1 is selected, but it was already selected. So now the CPU is ready to execute another instruction, but it's pretty much the same. Now what you saw, maybe, if you play along at home, which I don't expect you to do, but whatever, what you could see is that RAM cell 0 went from its initial state 0 to 1 to 0 and will become 1 and 0, etc., etc. So it toggles between 0 and 1. So what this program basically does is make the bit in RAM cell 0 toggle. Now if you have an LED memory mapped to RAM location 0, then the LED will flash. Now that's basically what this program does. The second RAM cell is only used as a temporary variable, because remember that the CPU has to invert a data bit each cycle. It cannot simply read a data bit, it has to invert it in order to read it and to respond to its value, to process its value. So if you look at this program, actually, you see that these two instructions here, if you look at the data address field of these two instructions, it's 1. So what these instructions basically do is swap the bit at RAM location 1, right? If it is 0 after the swap, go to program location 0, which is the first program location. If it was not 0 after this swap, simply go to the next instruction, which swaps it again. So if it was not 0 after this swap, it will be 0 after this swap, and the program will continue at program address 0 anyway. So what this basically does is a jump to program location 0. So it's a loop. So this is a very simple program to demonstrate how this works, so you get a feel for what the CPU does with the RAM and the ROM. So, and how simple it is also. Now, I hope you enjoyed this, and I hope it was clear. Let me think what you know. Let me know what you think. And yeah, please watch the other videos. And for more information, please see the Qibec site. That's qibec.org. It's also listed in the video description. Have a nice day. Thanks for watching, and goodbye.